Send a link to a friend or a loved one or a well-wisher. Okay, here we go. Chemistry 102, Section 175, Spring 2021, Chapter 10, An Introduction to Organic Chemistry. I'll be honest with you, this is one of the longer chapters that we do in this class. The introduction is a pretty long introduction, but what's good is that, for all the students who enroll in Chemistry 102, this isn't your first chemistry class now, is it? You all took Introduction to Chemistry 1, so there are many concepts that you would have learned in that class that are going to come in handy, right? Knowing the number of valence electrons from electron configuration, Lewis structures, right? These are things that are going to be really handy in chapter 10. So let's get started here. And what is organic chemistry? Well, organic chemistry is the study of molecules or compounds that contain carbon. Now, if you think about Introduction to Chemistry 1, you spent an entire semester discussing virtually the entire periodic table. You even covered nuclear chemistry in there, right? You talk about transition metals and all this. You talk about the S block, the P block, the D block, the F block, all these different elements. And then you take this one class, a whole semester that you just started, tonight, and the whole class is about one atom and the periodic table. Are you serious? Okay. We have over 100 elements, and you're going to teach me a whole semester about one atom? The answer is yeah. And the reason why we can do that, the reason why we can have an entire semester, even an entire year, dedicated to just the chemistry of carbon is because there are so many carbon-containing compounds. There are so many organic compounds. What's so special about carbon? Why can carbon form so many bonds? Well, let's take a look at the reasons. First of all, carbon can form stable covalent bonds with other carbon atoms. If you think about a lot of the other elements that you would have looked at, they don't form bonds with themselves. There are some that can, but not many can. And so carbon can form up to 4 covalent bonds with other carbon atoms. Let me prove it to you. Remember, carbon has 4 bonds. So if we have 1, 2, 3, 4 bonds to carbon like that, each one of those bonds could be to another carbon. Now, of course, since carbon has 4 bonds, each of these 4 carbons on the periphery has to have 3 more bonds, but the idea still stands, okay? Is that carbon, this carbon here in the center has 1, 2, 3, 4 covalent bonds to 1, 2, 3, 4 carbons. So that's really unique. Also, we're going to see that carbon can form chains, right? We can link all kinds of carbon atoms together like this. Now, that's not a complete structure, but the idea still stands that carbon can form what? A stable covalent bond with other carbon atoms. All right, number 2, carbon atoms can form stable bonds with other elements like oxygen, nitrogen, sulfur, the halogens. What are the halogens? Fluorine, chlorine, bromine, and iodine. And if you're wondering, is this an exhaustive list, Mr. Dion? Absolutely not. Carbon can form bonds with phosphorus and silicon, and it can do a lot of different things, okay? Now, these are the elements that are going to come up constantly: oxygen, nitrogen, sulfur, and the halogens. They will come up a lot in this class. But the presence of these and other elements confers many new physical and chemical properties on an organic compound. So that's just a sassy way of saying, well, because carbon can form bonds to all of these different elements, carbon can form a lot of different very interesting compounds. So that's another reason why we can spend a whole season, a whole semester studying the chemistry of carbon, organic chemistry. Number 3, carbon atoms can form double or triple bonds with other atoms to produce a variety of structures. Look at this here. We have, if we just examine these, look at this molecule. This carbon that I have highlighted in yellow has a double bond to another carbon. But if you look at the structure below, this carbon has a double bond to an oxygen. So, hey, carbon can form double bonds. This molecule here, and you don't need to know the name of this molecule for the first exam, but this is formaldehyde. Formaldehyde, which we will learn the name of later on, but just to put that, kind of bug in your ear. What else? Carbon can form triple bonds. Wow, look at this. A carbon having a triple bond with another carbon. Here's a carbon forming a triple bond with a nitrogen. Wow, carbon can do so many interesting things. And that is why we have so many carbon-containing compounds. And that's why we have to spend so much time talking about organic chemistry. What else? We're not done. Carbon can also arrange itself in other ways. It can form branched chains. It can form rings. It can form linear chains. Now, what's shown here, these 5 carbons all strung together, this would count as a linear chain, right? All the carbons are together in a row. You can probably guess that this ring here, that's a ring structure. Now, when it says a branched chain, what the heck is a branched chain? Well, a branched chain would be something like this. If I have a bunch of carbons in a chain like this, and then I have a branch going off like that, that's also a possibility for carbon. So again, the ways to arrange carbon with other atoms is pretty much or almost limitless. I'm going to the next bullet point here. It says 2 organic compounds may even have the same number and kinds of atoms, but they might have completely different structures and completely different properties. We call these compounds, we call these isomers. Now, I want to just give you a quick example before I move on. And there's not a lot of room on here. I should have given myself some more room, but isomers, okay? Let's say, for example, I have the formula C2H6O. What you're going to see is that there's more than one way to arrange those atoms into a structure, okay? Now, I'm just going to do this very quickly, but I can put the oxygen between the carbons like this, okay? And this is a perfectly legitimate Lewis structure. I'll even put the lone pairs on the oxygen. And I could also arrange C2H6O like this. Okay, again, I should have given myself a little bit more space. But these are 2 very different compounds. This one on the left-hand side, this is called dimethyl ether. It has a boiling point of around minus 24 degrees Celsius. And this one over here, this is ethanol. Ethanol has a boiling point of around 78 degrees Celsius. Okay, so look, boiling point, and this is just off the top of my head. I'm not sure if it's exactly 24 degrees Celsius. The boiling point of ethanol should be 78 degrees Celsius. But look, they're both made from the same elements, right? Both of these molecules are made from 2 carbons, 6 hydrogens, and 1 oxygen. But they have very different properties, don't they? We can see their boiling points are different. And if you're wondering, would they have different, other physical properties that would be different? Absolutely. They would have different densities, different refractive indices, different melting points, so on and so forth. So something else to think about. All right, let's go over a little bit of, content from Introduction to Chemistry 1, which you spend a lot of time talking about ionic bonds. So I'm not going to reteach ionic bonds, but you should know that there's a difference between ionic bonds and covalent bonds, isn't there? Right? Big difference. Well, inorganic compounds usually have ionic bonds. Not always, but usually they do. An example of an ionic bond would be the one in sodium chloride, right? You have a chloride with a negative charge. You have a sodium with a positive charge. What holds them together? What's the bond? Well, there's an electrostatic force between the positive charge on the sodium and the negative charge on the chloride. Okay, so that's an ionic bond. Whereas in organic chemistry, we're going to be speaking almost exclusively about covalent bonds, right? Organic compounds have covalent bonds. All right, let me give you an example. If I redraw one of those compounds from the last page, the dimethyl ether, every single one of the bonds in dimethyl ether is a covalent bond. The bonds between carbon and hydrogen, the bonds between carbon and oxygen, right? Those are all covalent bonds. So those are where 2 atoms share electrons, right? When we deal with an ionic bond, this is where we have electron transfer, right? Originally, you would have started with a sodium, right, and a chlorine, and the sodium has 1 unpaired electron, and the chlorine has, room for 1 more electron. So the sodium essentially gives up its electron, okay, to the chloride, to the chlorine to make chloride is what I should say. Anyhow, so that's electron transfer. And again, a covalent bond is the result of sharing electrons. All right. What else? Other differences between organic and inorganic compounds. When we think about organic compounds, you're going to hear me say the word molecule a lot in this class. Okay, we're going to talk about a lot of molecules. Just like that dimethyl ether, that was a molecule. Okay, organic compounds are also non-electrolytes. What's a non-electrolyte? It's something that is not going to ionize when it's placed in the solution, right? If you think about an electrolyte, if I have sodium chloride as a solid and I put it in water, what's it going to do? It's going to break apart into the sodium ion and the chloride ion, right? That's an electrolyte, sodium chloride, an inorganic compound, an ionic compound, okay? It dissociates into its ions. Whereas an organic compound, like dimethyl ether, if you put it in water, it is not going to dissociate. So that's another difference between organic and inorganic compounds. What else? Melting points and boiling points. Now this slide, you kind of have to take this with a grain of salt, but I would say that generally speaking, organic compounds, again, generally speaking, have lower melting points and lower boiling points than inorganic compounds do. And the reason why is because the forces that hold organic compounds together in a group, meaning if I have more than one molecule, the intermolecular forces are broken quite easily. And we're going to spend quite a bit of time talking about intermolecular forces. Whereas in an inorganic compound, they tend to have higher melting points, higher boiling points, because ionic bonds are very strong. They're stronger, generally speaking, than covalent bonds. All right, what about water solubility? Again, this is generally speaking. There are many exceptions to these rules, but a lot of organic compounds are nonpolar and are going to be insoluble in water, whereas a lot of inorganics will be water soluble, just like sodium chloride. Okay, just more food for thought. This table comes directly from the textbook, and it's nothing more than a comparison of the physical properties, or the major properties, I should say, of a typical organic and an inorganic compound. Okay, and they actually, there's some good rationale here. The two compounds that she picked are butane and sodium chloride. The reason why she picked these two is because they both have, look at their molar masses, 58 grams per mole and 58.5. So that's pretty close, right? They're very close to each other. Now, what's the point here? Sodium chloride, you know this from Introduction to Chemistry 1, is an ionic compound. Butane, you may not be familiar with, but I can help you out with butane. Here's the structure of butane. It's got 4 carbons. Each one of those carbons has a total of 4 bonds. Okay, like this. So this is just the Lewis structure of butane. You can see that there's nothing ionic in butane, right? Of course there isn't, because in order to have an ionic compound, you have to have a metal and a non-metal. Again, that's something you would have learned in Introduction to Chemistry 1. So let's take a look here. The type of bonding that's found in butane is going to be covalent bonding, right? It's all going to be the sharing of electrons. That means that every single one of these bonds, this bond, this bond, this bond, this bond, this bond, so on and so forth, all of those bonds represent 2 electrons that are being shared. Whereas in sodium chloride, it's ionic, right? And we discussed why that is. Well, the physical state of butane at room temperature, you probably know this already if you've ever used a butane lighter, just a regular Bic lighter. It's a gas at room temperature, isn't it? Right? So that tells you that the intermolecular forces that hold the molecules of butane together aren't very strong, are they? Whereas sodium chloride, because of those strong intermolecular forces holding those cations and anions together, since they're so strong, sodium chloride is a solid at room temperature. Now, I told you that generally speaking, the melting and boiling points of organic compounds are going to be lower than those of ionic compounds, and you can see that's definitely true. Here you see the boiling point of butane is lower than that of sodium chloride, much lower, 1,413.5 degrees lower. What else? The melting point is lower. Solubility in water, you can see that butane is insoluble in water. There's no reason why butane would dissolve in water. There's no way that it can interact with a water molecule. Whereas the ions in sodium chloride, those can interact with the dipole in water and they can dissolve. Butane is a flammable compound, as you know. Sodium chloride is non-flammable. So just things to think about. All right. Now, sodium chloride in the solid state does not conduct electricity, but when you have an aqueous solution of it, it will be an electrolyte. Anyhow, again, if you're like, what are we doing, Mr. Dion? All we're doing is kind of thinking about what you would have learned in Introduction to Chemistry 1, and we're kind of separating that, and I'm trying to show you what's different about organic chemistry from what you've already learned, okay? And if you're thinking, well, I already learned some of these concepts about organic chemistry already. I already learned about covalent bonds. Great, great. So then this would just suffice or serve rather. It's a little review for you. Okay, let's get really into getting some traction here. And we're going to start talking about a class of compound called hydrocarbons. And I bet you there's many students who are in class right now or are watching this video who have heard of hydrocarbons. Okay, you might have heard about them on the news. Most of the fuel that we put in our automobiles is made of hydrocarbons. Natural gas is largely made of hydrocarbons. And hydrocarbons, as you can probably guess, are compounds that contain only two elements, carbon and hydrogen, nothing else. So if you're thinking, hey, Mr. Dion, that butane molecule that you drew on the last slide, would that be a hydrocarbon? The answer is absolutely it is. It contains only carbon and hydrogen. Let's move forward. These are going to be nonpolar molecules. They're not soluble in water, but they're going to be soluble in typical nonpolar organic solvents. Now, it says here toluene and pentane. Now, if you're like, what the heck is toluene and pentane? Well, all you need to know right now is that toluene and pentane are both liquids at room temperature, so they're solvents, and they're both nonpolar organic solvents. Now, if you're not paying attention, I need you to wake up just for a second because I'm going to tell you something that's going to be important for you for the entire rest of this class. Until May, every single chapter is going to deal with this. If a hydrocarbon contains only carbon and hydrogen, there's only two possible types of bonds that you can have in a hydrocarbon. Only two. You can either have a bond between, carbon and carbon, or you can have a bond between hydrogen and carbon. Both of these bonds are non-polar bonds, okay? Those are non-polar bonds, okay? If we were in class, I would make you repeat after me. A carbon-carbon bond and a carbon-hydrogen bond are non-polar bonds. What do you know about water? Well, if you think about water, water is polar, right? This is, again, something you should have learned in Introduction to Chemistry 1, that water has a bent molecular geometry, and the oxygen has a delta minus, the hydrogens have a delta plus. You could draw the dipole going in, let me get a different pen here, in this direction. So water is a polar compound. And you probably remember the rule that like dissolves like. And so non-likes are not going to dissolve. So since hydrocarbons are nonpolar and water is polar, that is why hydrocarbons are not going to dissolve in water. Now, if you think about something, another hydrocarbon that you would know would be something like octane. Octane is a component of gasoline, okay? And if you've ever spilled gasoline, has anybody ever spilled gasoline on a puddle before? You'll notice that the gasoline kind of pools on the top. It doesn't dissolve in the water. If you've ever seen an oil spill or seen the footage of an oil spill, you know that the oil floats on top of water. Why? Because the oil is a hydrocarbon. It is nonpolar. It is not going to mix with water. If you've ever tried to mix cooking oil, right, with water, the reason why cooking oil or vegetable oil is not going to dissolve in water is cooking oil or vegetable oil is not a hydrocarbon, but it is largely nonpolar. Okay, so something to think about, right? Oil and water don't mix. Okay, there's going to be a barrier there. Anyhow, all right, give me a thumbs up if you follow me thus far, just where we've gotten to. It's 6:30. You're like, you know what, Mr. Dion, I'm with you so far. You can just give the thumbs up in the chat if anybody's there. Yeah, all right, thanks, Lisa. Good, I'll take it. All right, one student, that's good enough for me. Let's keep moving. All right, so hopefully you're with me. And if you're like, I'm a little confused, Mr. Dion, what would you want to do? Well, some courses of action that you could take would be read the textbook before coming to class, watch the videos that I have posted to my YouTube channel. If you want to rewatch this video, feel free to do that. Try some practice problems from the book. But right now we're just talking about hydrocarbons. So let's continue on with our discussion on hydrocarbons. It says here that hydrocarbons are constructed of chains or rings of carbons with sufficient hydrogen atoms to fulfill a carbon's need for 4 bonds. So remember, the carbon always has to have 4 bonds. Okay, carbon is always going to have 4 bonds. All right. A substituted hydrocarbon is one in which one or more of the hydrogen atoms is replaced by another atom or a group of atoms. So we're going to see examples of hydrocarbons constructed of chains, and we'll also see examples of substituted hydrocarbons. Well, let's take a look at a little diagram here that I have, okay? And this is actually the whole family of hydrocarbons, okay? It's a little more complicated than just saying, okay, there's just hydrocarbons. Well, there's actually a bunch of different types of hydrocarbons, all right? The first division that you can make between hydrocarbons is you can have what's called aliphatic, and you can have what are called aromatic. We're not going to stress about aromatic hydrocarbons immediately, but I guess we will be looking at them tonight to some degree. But I'll just say that the aromatic compounds, those are a very specific group of hydrocarbons. Now, in terms of aliphatic, so compounds that are not aromatic, we can divide them up into alkanes and cycloalkanes, alkenes and alkynes. All right, let me explain to you the difference between an alkane, a cycloalkane, an alkene, and an alkyne. So try to follow with me here. The first thing is that an alkane only contains single bonds, nothing but single bonds. Now, I showed you earlier on that carbon can form double and triple bonds, can it? But if your molecule only has single bonds, then, my friend, you have an alkane. If you have a compound that has only single bonds, but it's got a ring in it, then it's not just an alkane. If it's got a ring, you call it a cycloalkane. So here's an example of a cycloalkane shown here. If you have a double bond in your compound, okay, and we're going to see many organic compounds that have double bonds, we call those alkenes. So again, it's got to have a double bond. When it's a double bond, it's called an alkene. And when you have at least one triple bond, okay, if you've got a triple bond in an organic compound, then it's called an alkyne, okay? And again, I'll talk to you about what an aromatic compound is more later, but an aromatic compound generally has alternating single and double bonds. All right. Well, let's talk a little bit more about hydrocarbon saturation and alkanes, alkenes, and alkynes. Now, an alkane, since alkanes only have single bonds, alkanes are compounds that contain only carbon-carbon and carbon-hydrogen single bonds, right? So in an alkane, the only thing you're ever going to see in an alkane is a carbon-carbon single bond and a carbon-hydrogen single bond. Nothing else. You know that those are nonpolar bonds. I already told you that, okay? Just to reiterate, a saturated hydrocarbon has no double bonds and no triple bonds, all right? So an alkane will never have a double or a triple bond. Whereas an alkene and alkyne, we call those unsaturated compounds. Before I get into that a little bit more, let's talk about what a saturated hydrocarbon is. If I have 3 carbons, okay, and I put all those 3 carbons in a row like I have shown here, that I put in the blue box. Remember that carbon has to have 4 bonds. If I maximize the total number of bonds that each one of these carbons can have, that is when I have a saturated hydrocarbon. If I have a double or a triple bond in my molecule, then it's called an unsaturated hydrocarbon. Why? Because it doesn't have the maximum amount of bonds that are possible for all of the carbons in the molecule. Okay, so that's what an unsaturated hydrocarbon is. Now, you've probably all heard of saturated fats and unsaturated fats. Well, that's actually related to the concepts of a saturated hydrocarbon and an unsaturated hydrocarbon. Now, again, a fat is not a hydrocarbon, but it's related to this concept, and we will look at it later on. Give me a thumbs up if you follow me on a saturated hydrocarbon and an unsaturated hydrocarbon having a double or a triple bond. It doesn't have the maximum number of bonds to hydrogen. Is anybody with me on that? Or anybody have any questions? All right. Okay, good. Well, let's move on from there and let's talk about cyclic hydrocarbons. Okay. Now, if we go back here, there are 2 types of cyclic hydrocarbons, aren't there? right? This is a cyclic hydrocarbon, a cycloalkane. And aromatics, you can see, you're like, what's this funny looking, circle inside a hexagon? Well, I'm going to talk more about that later. But these are both cyclic hydrocarbons, aren't they? Okay. Well, let's look at the difference between a cycloalkane and an aromatic compound. And that's shown right here. If I have 6 carbons in a ring, okay, that's what I have here. 1, 2, 3, 4, 5, 6 carbons all in a ring. And I give each one of those carbons the maximum number of single bonds. Well, if I just hone in on one of these carbons, since this carbon has a bond here and a bond here, that means it's going to have 1, 2 more bonds. So this compound is a cycloalkane. This is called cyclohexane. Its molecular formula is C6H12. If I look at benzene, benzene is aromatic. Okay, what makes it aromatic? The reason that it's called aromatic is because you see you have a double bond, single bond. Double bond, single bond, double bond, single bond. So the double and single bonds are alternating. When I have 6 carbons in a ring like this, and the double and single bonds are alternating, you, my friend, have an aromatic compound. Okay? Now, if I just hone in on one of the carbons in benzene, which again is an aromatic compound, you can see this carbon is a double bond and a single bond here. So that means that each one of these carbons can only be bound to one hydrogen. And benzene's molecular formula is C6H6. Now let me tell you a little bit more about aromatic compounds, and we'll talk a lot about aromatic compounds in this class. Aromatic, what does aromatic mean? Now, if I heard the word aromatic for the first time in a chemistry class, I would assume, and rightfully so, that it probably has something to do with odor. You might think, okay, well, an aromatic compound, maybe it has some kind of, wonderful fragrant odor. Well, the answer is the first aromatic compounds that were isolated by scientists did come from sweet-smelling tree resins and saps. That's where the first aromatic compounds were isolated from. But since then, we've discovered many more aromatic compounds, many of them that don't smell good at all, and many that have no odor at all, many that are odorless. And so nowadays, what we refer to when we say aromatic compound, aromatic actually means really stable, okay? Aromatic compounds are very stable compounds. Doesn't mean they're completely unreactive, but they are quite stable. And we'll talk more about that later in the class. So what have we covered so far? We've covered saturated hydrocarbons, alkanes. They have the maximum number of single bonds. We've covered alkenes and alkynes, and we've said those are unsaturated hydrocarbons because they have a double bond or a triple bond. And now we're talking about cyclic hydrocarbons. And we said we can have a cycloalkane like cyclohexane, and we can have an aromatic compound like benzene. And the difference between these is that in the aromatic compound, the 6 carbons in the ring alternate double and single bonds between the carbon atoms. All right, so now we're going to switch gears quite a bit. Okay, we're going to switch gears pretty good. We're not going from first to second. We're going from first to like H. We're going to a completely different gear system here. And we're going to talk about functional groups for a few minutes. Let me just double check here. So this is probably your first big, memorization assignment in Chemistry 102 is memorizing the common functional groups. A few semesters ago, I put together a video where I cover all of the functional groups in a lot of detail, okay? Even more of the functional groups that are found on this slide. But on your first exam, you are going to have to know all of these functional groups, okay? Now, the way that the functional groups are laid out in this table is not really the way that I like it. I'll just explain what I mean by that. Is where she says functional group here under this heading, she says hydroxyl carbonyl, right, carboxylate amino. I don't really like that. What I like is instead of the type of compound, I usually call these the functional groups. So a functional group would be an alcohol, an aldehyde, an amide, an amine, a carboxylic acid, an ester, an ether, a halide, a ketone, an alkene, and an alkyne. And that's the vernacular that we're going to use in this class, okay? And if you're like, oh, Mr. Dion, is this just your personal thing? No, if you actually go on YouTube and look at other videos or look at other textbooks, the first column is what we call the functional groups. And you are responsible, again, for knowing all of these functional groups. Okay? So you are responsible for knowing all of these for the first exam. Let's go over them kind of quickly here. So take a deep breath. Okay, it's going to require a deep breath before we get cooking here, and we'll talk about all of the functional groups. Now, before we do that, I want to mention this element R. You probably noticed there's, hey, what's this R? I don't see any R on the periodic table. Well, R is commonly used in organic chemistry. Some people say it means remainder, like the rest or the rest of a compound. But if you look down here, she gives you a little explanation as to what R means. It says here that R and R prime represent an alkyl group, an aryl group, or a hydrogen. In a ketone, the R and the R prime must be alkyl or aryl groups. Well, if you're like, what the heck is an alkyl group? I don't even know what that is yet, Mr. Dion. Well, the idea is nothing more than it's just the rest of a compound. So let me explain it to you, and then hopefully it'll become a little more clear. The bottom line is this, and we'll start with the first one here, an alcohol. If you see an oxygen bound to a hydrogen like this in a compound, in an organic molecule, you've got an alcohol. In fact, you even saw one earlier this evening. I drew you the structure of ethanol, didn't I? I said that it was CH3, right? CH2, and then I put oxygen, and then I put hydrogen. So look, you can see there's an oxygen bound to a hydrogen, and it's bound to all of this. This big part here, you would call that the R. So to abbreviate that, we just say ROH. So when you see the OH bound together like that, that's what we call an alcohol. So that's how you know you have an alcohol. If you have an aldehyde, it's in a compound where you have a carbon with a double bond to an oxygen, and the carbon is also bound to a hydrogen. If you have an amide, it's when you have a carbon doubly bound to an oxygen, and the carbon is also attached to a nitrogen. If you have an amine, it's when you have your R group attached directly to a nitrogen. If you have a carboxylic acid, it's when you have a carbon doubly bound to an oxygen, and then you also have an oxygen and hydrogen bound to it, like that. If you have an ester, it looks pretty close to a carboxylic acid. You have a carbon doubly bound to oxygen, then a single bond to oxygen, and then another R group attached. If you have an ether, you have an oxygen between two R groups. They can be the same, they can be different, it doesn't matter. If you have a halide, you can imagine that that's when you have a compound, an organic compound that is attached to a halogen. If you have a ketone, that's when you have a carbon with a double bond to oxygen and it's between two R groups. And then an alkene and an alkyne, we've already kind of covered these. An alkene is when you have a double bond between two carbons, and an alkyne is when you have a triple bond between two carbons. I know I went over that very, very quickly, but what I'm going to encourage you to do before coming to our next lecture on Monday evening is to look over these functional groups and to watch the video that I'm going to post in our announcements on D2L after lecture tonight. And I'm going to start lecture on Monday with a couple practice problems. I'm going to draw some molecules and get you to identify the functional groups in those molecules. And if you're wondering, oh, Mr. Dion, that seems like a lot of work to try to memorize all this stuff, before the next class. Well, the good news is if you think back to the schedule that we looked at, our lecture schedule, you probably noticed that we do a whole chapter where we talk about carboxylic acids, a whole chapter where we talk about amines and amides, right? So all of these functional groups are going to keep coming up constantly in organic chemistry. Okay, let me encourage you again. Look, if you think about anything you've learned anywhere in your life, whether it was in school or not, there's always sort of a language associated with any subject that you learn. And organic chemistry is like any other subject in that you have to learn sort of the vernacular and the terminology that goes along with the subject before you can really start to understand the subject. And that's why The author of our textbook introduces functional groups in table 10.2 right away. Right at the start of organic chemistry, she says it's imperative that you learn your functional groups. All right, well, let's move on from there, and we can talk about alkanes for a second.